Have you ever stood at the edge of the ocean and wondered what lies beneath those endless waves? Most of us look out at that vast expanse of water and think we understand its scale, but the truth is, the ocean is so impossibly deep that it defies everything we think we know about our planet. If you took every mountain peak, every towering skyscraper, every piece of land that rises above sea level on Earth, and crushed it all down to fill the deepest parts of our oceans, the entire planet would still be covered by water. Not just covered, but submerged under a global ocean that stretches 2 miles deep in every direction. Think about that for a moment. Every continent, every island, everything we call home would disappear beneath the waves. 3/4 of our planet is already covered by water, but what most people don't realize is just how much deeper it gets beyond those 2 miles. Today, we're going to take a journey into the abyss, descending through layers of our ocean that most humans will never see, encountering creatures that seem pulled from nightmares, and discovering depths so extreme that they challenge the very limits of human exploration. But before we dive into the unknown, let me give you some perspective on just how small we really are in this underwater world. This tiny dot represents the average human being, barely visible, isn't it? This slightly larger dot shows the size of an elephant, one of the largest land animals on our planet. And this much bigger shape represents the Nevis, the largest ship ever constructed by human hands, stretching over 1,000 feet from bow to stern. Now, with those reference points in mind, let's descend beneath the surface and see what awaits us in the depths. Our first landmark sits just 40 meters below the surface. This might not sound like much, but it represents the maximum depth allowed for recreational scuba diving. At this shallow depth, sunlight still filters through the water, creating those beautiful underwater scenes you've seen in documentaries. The pressure here is manageable, the water relatively warm, and marine life abundant. But let's keep going deeper. At 93 meters down, we encounter something fascinating and haunting. This is where the wreck of the Lusitania was discovered, that infamous passenger liner that was torpedoed during World War I. Here's what makes this discovery so remarkable. The Lusitania itself was 240 meters long, which means this massive ship sank in water that was actually shallower than the ship's own length. If the vessel had somehow landed upright on the ocean floor, a significant portion would have jutted above the surface like some ghostly monument to maritime tragedy. Just 7 meters deeper, at the 100-meter mark, we reach a critical threshold. This is where diving becomes genuinely dangerous without proper precautions. The water pressure at this depth can cause nitrogen narcosis, a condition that impairs judgment and can prove fatal to unprepared divers. Yet this danger hasn't stopped some extraordinary individuals from pushing even further into the depths, using nothing but their own lungs and determination. Meet Herbert Nitsch, a man who redefined what we thought was humanly possible. This Austrian free diver holds the world record for the deepest dive on a single breath, reaching an astounding depth of 214 meters. Picture this. Nitsch descended to this crushing depth, where the pressure is over 20 times what we experience at sea level, held his breath the entire time, and then swam back to the surface, all without any breathing apparatus whatsoever. But even Nitsch's incredible achievement is dwarfed by the world record for deep-sea diving with equipment. At 332 meters below the surface, we find the mark set by Ahmed Garber, an Egyptian technical diver who spent years preparing for this single, death-defying descent. To put this in perspective, if Garber had gone just 111 meters deeper, he would have reached the height of the Empire State Building if it was somehow submerged beneath the waves. As we continue our descent to 500 meters, we enter the realm of the ocean's largest inhabitants. This is the maximum depth that blue whales, the largest creatures ever to exist on our planet, can withstand. These magnificent giants, with hearts the size of small cars and tongues that weigh as much as elephants, represent the absolute pinnacle of marine life. At this same depth, we also find the operational limit of military submarines, like the USS Seawolf, one of the most advanced underwater vessels ever constructed. 535 meters down brings us to the deepest diving birds on Earth. Emperor penguins, those remarkable Antarctic dwellers, can plunge to these depths in their relentless search for food. But consider the crushing force they endure. At this level beneath the surface, the water pressure pressing down on these birds equals approximately the weight of a polar bear standing on a single quarter. Every square inch of their bodies experiences this incredible force, yet they navigate these depths with graceful precision. At 830 meters, we reach a depth equivalent to the height of the Burj Khalifa in Dubai, the tallest building humanity has ever constructed. If this architectural marvel were somehow inverted and plunged into the ocean, its spire would rest at this depth while its base disappeared into the darkness below. But it's at the 1,000-meter mark where our journey truly begins to get terrifying. Once you descend past 1,000 meters below the surface, you enter what marine biologists call the midnight zone. Here, in this alien realm, sunlight cannot penetrate. Every inch of ocean below this point exists in perpetual, absolute darkness. The kind of darkness that's impossible to imagine unless you've experienced it yourself. It's not just the absence of light, it's the presence of an emptiness so complete that it seems to press against your consciousness. The water pressure at this depth would be like standing on the surface of Venus, where the atmospheric pressure is 90 times greater than Earth's. A human body exposed to this pressure without protection would be crushed instantly, compressed into something unrecognizable in a matter of milliseconds. Yet life persists here, and not just any life, but some of the most bizarre and terrifying creatures our planet has ever produced. This is where you might encounter the giant squid, those legendary monsters of the deep that have inspired countless maritime legends and nightmares. These creatures, if the crushing pressure doesn't kill you first, represent a very real threat to anything unlucky enough to cross their path in these lightless depths. At 1,280 meters, we find the maximum diving depth of leatherback sea turtles, the largest turtles on Earth. These ancient mariners, whose species has remained virtually unchanged for over 100 million years, somehow navigate these crushing depths as part of their daily existence. 1,828 meters down, and we've reached a depth equivalent to the deepest part of the Grand Canyon. If you stood at the bottom of that famous geological wonder and looked up, you'd be seeing the same distance that separates us from the surface at this point in our oceanic descent. But we're just getting started with the true horrors that await us in the deep. At 2,000 meters below the surface, we begin encountering some of the ocean's most nightmarish inhabitants. The black dragonfish lurks at these depths, a carnivorous predator perfectly adapted to hunt in a world where no light has ever shone. These creatures exist in complete darkness, and the only way you would ever see one is with a powerful flashlight piercing through the eternal night of the deep ocean. 2,250 meters brings us to the maximum depth of both sperm whales and the colossal squid, two titans locked in an eternal battle in the abyss. Sperm whales, the largest toothed predators on Earth, regularly bear scars and wounds across their massive bodies from combat with these enormous cephalopods. At these crushing depths, the colossal squid can grow to lengths of 14 meters and weigh up to 750 kilograms. Their eyes, the largest in the animal kingdom, measure the size of dinner plates, perfectly evolved to capture any trace of light in this dark realm. Their tentacles are armed with rotating hooks, sharp as razors, and strong enough to slice through whale flesh like butter. So yes, good luck with that encounter in the pitch-black depths of the ocean. Much further down, at 3,800 meters, we discover one of the most famous underwater landmarks in human history. The wreck of the Titanic, that supposedly unsinkable ship now rests in eternal darkness, slowly being consumed by the crushing pressure and unique bacteria that exist only in these extreme depths. At 4,000 meters below the surface, we officially enter what oceanographers call the abyssal zone. The water pressure here reaches 11,000 pounds per square inch. To put that in perspective, it's like having the weight of 3 cars pressing down on every square inch of surface area. This is where we find some of the strangest creatures imaginable: the fang-toothed fish with its nightmare-inducing teeth, the anglerfish with its glowing lure, and the gulper eel that can unhinge its massive jaw to swallow prey larger than itself. These aren't just unusual animals, they're alien life forms that happen to share our planet. 4,267 meters down represents the average depth of the world's oceans. This is where most people would expect to hit the ocean floor, where the journey would end. But there are parts of our ocean that plunge far, far deeper than this average depth, into realms so extreme that they challenge everything we know about life on Earth. At 4,791 meters, we encounter the wreck of the Bismarck, that legendary German battleship that met its fate during World War II. Even this massive warship, once the pride of the German Navy, now sits crushed and broken in the eternal darkness of the deep ocean. 6,000 meters below the surface marks the beginning of the Hadal Zone, named after Hades, the ancient Greek underworld. The water pressure at these depths becomes 1,100 times greater than what we experience on land. That's equivalent to an elephant standing on a postage stamp, or one person trying to support the weight of 50 Boeing 747 jumbo jets. At these crushing depths, the pressure would be instantly fatal to any human without external protection. Yet, incredibly, life still exists here in forms so bizarre they seem pulled from science fiction. 6,500 meters down, we reach the maximum depth of the DSV Alvin, the submersible that helped discover the Titanic wreck. This remarkable vessel represents the absolute limit of human deep-sea exploration technology, yet it can only scratch the surface of the ocean's true depths. Much further down, at 8,848 meters beneath the surface, we would reach the height of Mount Everest if it were flipped upside down and submerged underwater. Think about that. The tallest mountain on our planet could be completely hidden beneath the ocean's depths, with room to spare. At 10,898 meters down, we reach the depth achieved by filmmaker James Cameron in 2012 during his historic deep-sea challenge expedition. Cameron descended alone in a specially designed submersible to depths, where the pressure could crush a human body in microseconds, all in the name of scientific exploration and human curiosity. But even Cameron's remarkable achievement wasn't the deepest humans have ever ventured into the abyss. That record belongs to 2 men named Don Walsh and Jacques Picard, who in 1960 descended to a depth of 10,916 meters using the bathyscaphe Trieste. Their journey took 5 hours to descend through the crushing depths of the ocean, and they remained at the bottom for only 20 minutes before a window crack forced them to begin their ascent to the surface. Just slightly deeper than their historic dive, at 10,972 meters, we reach the average cruising altitude of a commercial airliner. If you've ever looked out an airplane window during a flight and gazed down at the earth below, that gives you an excellent sense of the abyss we're currently exploring. We're as far below the ocean surface as you are above the ground during a typical flight. Finally, at 10,994 meters below the surface, we reach the deepest known point in our ocean, Challenger Deep. Located in the Mariana Trench, just 300 kilometers southwest of the island of Guam, this represents the absolute bottom of the world as we know it. Yet even this record-breaking depth may not tell the complete story of our ocean's mysteries. Scientists believe there may be places even deeper than Challenger Deep that have yet to be discovered. In 1997, researchers found Sirena Deep at 10,732 meters, making it the second deepest known point in our ocean. Here's what's truly staggering. We estimate that only 5% of our oceans have been explored and mapped. That leaves 95% as a complete mystery, an underwater universe that remains as unknown to us as the surface of distant planets. It may only be a matter of time before we discover even deeper parts of our ocean, depths that will challenge everything we think we know about our planet and the life it supports. But what makes these depths even more mind-boggling is when you start to consider the creatures that somehow manage to survive in this crushing void. Remember, we're talking about pressures that would instantly kill any surface dweller, temperatures hovering just above freezing, and complete darkness that has existed since the dawn of time. Yet down in these impossible depths, life finds a way. The creatures living in the deepest parts of our ocean have evolved into forms so alien that they seem like they belong on another planet entirely. Take the snailfish, for example. These ghostly white creatures have been found living at depths exceeding 8,000 meters, deeper than Mount Everest is tall. Their bodies are made almost entirely of a gel-like substance that somehow maintains its structure under pressures that would crush steel submarines like empty soda cans. These deep-sea snailfish don't have the rigid bone structure that surface fish possess. Instead, their skeletons are made of cartilage, flexible enough to compress under the enormous pressure without breaking apart. They move through the water like living ghosts, feeding on tiny crustaceans and organic matter that drifts down from the world above like snow falling in slow motion. But perhaps even more remarkable are these xenophyophores, single-celled organisms that can grow to the size of dinner plates. Yes, you heard that correctly. These are individual cells, not colonies, not multicellular organisms, but single cells that have somehow grown to enormous proportions in the crushing depths of the ocean floor. They represent some of the largest single-celled organisms ever discovered, and they thrive in conditions that would be instantly lethal to virtually every other form of life on our planet. The deeper we go, the stranger things become. At the very bottom of Challenger Deep, scientists have discovered microbial life forms that exist in ways that completely rewrite our understanding of biology. These microorganisms don't rely on sunlight for energy like virtually every other living thing on Earth's surface. Instead, they derive their energy from the chemicals seeping out of underwater volcanic vents, creating entire ecosystems based on processes we're only beginning to understand. These deep-sea volcanic vents, called hydrothermal vents, create oases of life in the deepest parts of our ocean. The water around these vents can reach temperatures of over 400 degrees Celsius, hot enough to melt lead, yet somehow life flourishes in these extreme conditions. Giant tube worms, some reaching lengths of 8 feet, cluster around these vents like alien flowers blooming in hell itself. The tube worms have no mouths, no stomachs, no digestive systems as we understand them. Instead, they rely on symbiotic bacteria living inside their bodies to convert the toxic chemicals from the vents into usable energy. It's a form of life so fundamentally different from everything we see on the surface that it's forced scientists to reconsider what we even mean when we talk about life itself. But here's what's truly unsettling about these depths. We know more about the surface of Mars than we do about the deepest parts of our own oceans. We've mapped every crater on the Moon with incredible precision, but vast sections of our ocean floor remain complete mysteries. There could be mountain ranges down there, larger than the Himalayas, canyons deeper than the Grand Canyon, and ecosystems more diverse than the Amazon rainforest, and we would have no idea they exist. The technology required to explore these depths pushes the absolute limits of human engineering. The submarines that can reach the deepest parts of our ocean are marvels of technology, built with walls several inches thick and designed to withstand pressures that would crush a normal submarine instantly. The viewing windows on these vessels are made of specially engineered materials that can maintain their integrity under crushing forces that defy imagination. Consider this. When James Cameron made his historic dive to Challenger Deep, he was sitting inside a sphere that was being compressed by the equivalent weight of 14 Eiffel Towers, pressing down on every square metre of use as surface area. The slightest structural flaw, the tiniest imperfection in the vessel's construction, would have resulted in instantaneous death as the submarine imploded faster than the human nervous system could even register what was happening. The journey to these depths isn't just about distance, it's about travelling through layers of water that become increasingly hostile to human life. As you descend, the temperature drops steadily until you're surrounded by water that's barely above freezing. The darkness becomes so complete that it's not just an absence of light, but a presence unto itself, pressing against your consciousness in ways that can drive people to madness. Professional deep-sea explorers often describe the psychological effects of descending into these depths. The human mind, evolved to exist in a world of light and familiar pressures, struggles to cope with the alien environment of the deep ocean. Some describe feeling like they're falling through space. Others report a crushing sense of isolation that goes beyond anything experienced on the surface. But perhaps the most disturbing aspect of these depths is how they challenge our basic assumptions about our planet. We think of Earth as a world dominated by land and sky, by forests and mountains and familiar landscapes. But the truth is, our planet is an ocean world. The vast majority of livable space on Earth exists in these crushing depths, in darkness so complete that it makes the coldest, most remote corners of Antarctica seem like tropical paradises by comparison. The ocean's deepest trenches aren't just geographical features. They're alien worlds that happen to exist on our own planet. They're places where the normal rules of physics and biology are pushed to their absolute limits, where life exists in forms so bizarre that they expand our understanding of what's possible in the universe. And here's the most mind-bending part. We've barely scratched the surface of exploring these depths. Every expedition to the deep ocean reveals new species, new geological formations, new mysteries that challenge everything we thought we knew. Scientists estimate that we've identified less than 20% of the species living in our oceans, and the deeper we go, the more alien and impossible these creatures become. The bioluminescence alone in these depths creates light shows that would put any aurora borealis to shame. Creatures generate their own light through chemical reactions, creating displays of blue, green, and red that flash and pulse through the darkness, like living constellations. Some deep-sea creatures use this light to communicate, others to hunt, and still others to confuse predators in ways that seem pulled from the pages of science fiction. Imagine descending into these depths and suddenly finding yourself surrounded by thousands of jellyfish, each one glowing with its own internal light, creating a living galaxy in the crushing darkness of the deep ocean. Or picture encountering a giant siphonophore, a creature that can stretch for lengths of over 40 meters, longer than a blue whale, creating chains of light that snake through the darkness like living lightning. These aren't just rare occurrences, they're the normal state of existence in the deep ocean. Down in these crushing depths, bioluminescence isn't unusual, it's practically universal. Nearly every creature living in the deep ocean has evolved some way to create its own light, turning the darkest parts of our planet into alien light shows that no human eyes were ever meant to see. The pressure at these depths doesn't just affect living creatures, it fundamentally changes the nature of water itself. At the deepest parts of our ocean, water becomes denser, heavier, almost syrup-like in its consistency. The normal properties we associate with water, its fluidity and lightness, become altered under pressures so extreme that they approach the conditions found at the core of planets. Yet somehow, in this alien environment that seems hostile to every form of life we understand, entire ecosystems thrive. Food webs exist that are completely independent of sunlight, based instead on the chemical energy seeping from the Earth's core through underwater volcanic activity. It's like discovering that our planet has been harboring alien civilizations in its deepest places all along. The strangest part about these deep ocean ecosystems is how they operate on timescales that make human civilization seem like a brief flicker. The organic matter that drifts down from the surface, what marine biologists call marine snow, can take weeks or even months to complete its journey to the ocean floor. This slow-motion blizzard of dead plankton, fish scales, and other organic debris creates the primary food source for many deep-sea creatures. But here's what makes it even more surreal. Some of the creatures living at these depths have lifespans that stretch across centuries. Deep-sea corals, growing in complete darkness and crushing pressure, can live for thousands of years. These ancient organisms have been filtering nutrients from the water since before human civilization began, creating underwater forests that exist in perpetual night. The Greenland shark, one of the longest living vertebrates on Earth, regularly ventures into these extreme depths. Some specimens have been carbon dated to over 400 years old, meaning there are sharks swimming in our oceans today that were alive when Shakespeare was writing his plays. These massive predators, reaching lengths of 24 feet, move through the deep ocean like living ghosts from another era. At depths beyond 6,000 meters, we enter a realm where the very concept of seasons becomes meaningless. The water temperature remains constant year-round, hovering just above freezing. There's no day or night cycle, no changing weather patterns, no seasonal migrations. It's a world locked in eternal winter, where time moves differently than anywhere else on our planet. The Hadal zone, those depths below 6,000 meters, represents less than 1% of the ocean's total volume, yet it may contain some of the most extreme life forms on Earth. The pressure here is so intense that it would compress a human body to the size of a marble in milliseconds. Yet researchers have discovered amphipods, tiny shrimp-like creatures, thriving at depths exceeding 10,000 meters. These Hadal amphipods have evolved into living pressure chambers, their bodies specially adapted to exist under forces that would instantly destroy any surface-dwelling creature. They scavenge the ocean floor for any organic matter that manages to drift down from the world above, competing for resources in an environment where every calorie of energy is precious beyond measure. But perhaps the most mind-bending discovery in these depths is the existence of what scientists call barophilic bacteria. These microorganisms don't just tolerate the crushing pressure of the deep ocean, they actually require it to survive. If you brought these bacteria to the surface, they would die from the lack of pressure, essentially exploding from the inside out as their cellular structure fails without the crushing force they've evolved to depend on. This completely flips our understanding of life on its head. We think of pressure as something that destroys life, but in the deepest parts of our ocean, pressure becomes the very foundation that life depends on. These bacteria represent a form of existence so alien that they might as well be from another planet entirely. The geological features at these depths are equally mind-boggling. The Mariana Trench, where Challenger Deep is located, isn't just a single depression in the ocean floor. It's a massive geological system stretching over 1,500 miles, longer than the entire California coastline. The trench was formed by the collision of massive tectonic plates, creating a scar in the Earth's crust that plunges deeper than Mount Everest reaches into the sky. But the Mariana Trench isn't alone in its extreme depths. The Tonga Trench in the Pacific reaches depths of over 10,000 meters, while the Puerto Rico Trench in the Atlantic plunges to depths that would swallow the tallest mountains on Earth without a trace. These underwater canyons represent some of the most extreme environments on our planet, places where the normal rules of physics and biology are pushed to their absolute breaking point. The water at these depths moves in ways that seem to defy logic. Deep ocean currents, driven by differences in temperature and salinity, create underwater rivers that flow along the ocean floor for thousands of miles. These currents are so powerful that they can carry sediment and nutrients across entire ocean basins, creating highways of life in the deepest parts of our planet. One of the most fascinating aspects of these deep ocean currents is how they connect the deepest parts of our ocean with the surface world. Water that sinks to the bottom of the ocean in the polar regions can take over 1,000 years to complete its journey through the deep ocean currents before eventually rising back to the surface. This means that some of the water in the deepest parts of our ocean has been travelling through the darkness for longer than recorded human history. The chemical composition of water at these depths is fundamentally different from surface water. The intense pressure causes gases to behave in unusual ways, creating concentrations of dissolved minerals and chemicals that would be impossible at the surface. Some deep-sea environments contain water that's so saturated with hydrogen sulfide that it would be instantly toxic to any surface-dwelling creature. Yet in these chemically hostile environments, life has found ways to not just survive, but thrive. Chemosynthetic bacteria convert these toxic chemicals into energy, creating the foundation for entire ecosystems that exist completely independent of the sun. These bacterial mats cover vast areas of the deep ocean floor, creating underwater prairies that stretch for miles in every direction. The creatures that feed on these bacterial mats have evolved into forms that seem pulled from nightmares. Giant isopods looking like enormous pillbugs can grow to lengths of 20 inches and scavenge the ocean floor for any organic matter they can find. These armoured scavengers can survive for years without food, entering a state of near-suspended animation until their next meal arrives. Deep-sea gigantism is a phenomenon that occurs throughout these extreme depths. Creatures that are small at the surface grow to enormous proportions in the deep ocean. Giant spider crabs with leg spans reaching 12 feet patrol the ocean floor, like underwater tarantulas. Colossal squid with eyes the size of dinner plates and tentacles armed with rotating hooks represent the largest invertebrates on our planet. The vampire squid, despite its terrifying name, represents one of the most bizarre adaptations to deep-sea life. This creature can literally turn itself inside out when threatened, exposing sharp spines that make it impossible for predators to swallow. It exists in a state between squid and octopus, representing an evolutionary path that diverged millions of years ago in the crushing depths of the ocean. But it's not just the creatures that are strange at these depths. The very nature of sound behaves differently in the deep ocean. The intense pressure and cold temperatures create acoustic conditions that allow sounds to travel for thousands of miles underwater. Whale songs can cross entire ocean basins, creating a global communication network that spans the deepest parts of our planet. The Sofar Channel, a layer of water at depths between 700 and 1,300 meters, acts like an underwater highway for sound. Military submarines use this acoustic channel to communicate across vast distances, but it's also used by marine life in ways we're only beginning to understand. Some scientists believe that deep-sea creatures use these acoustic channels to communicate across distances that would be impossible at the surface. The bioluminescent displays in these depths aren't just beautiful, they're essential for survival. In a world where vision is limited to the range of whatever light a creature can produce, bioluminescence becomes the primary means of communication, hunting, and defense. The deep ocean is filled with creatures that can produce light displays more complex than anything we see on land. Some deep-sea creatures have evolved multiple types of bioluminescence, creating light shows that serve different purposes. Counterillumination helps creatures blend in with the faint light filtering down from above, while ventral photophores create patterns that can confuse predators or attract prey. The deep ocean becomes a living constellation, with creatures flashing and pulsing in patterns that create an underwater aurora. The anglerfish represents perhaps the most famous example of deep-sea bioluminescence. These nightmare creatures dangle glowing lures in front of their massive mouths, attracting prey in the darkness before swallowing them whole. But the anglerfish's reproductive strategy is even more bizarre than its hunting technique. Male anglerfish are tiny compared to females, and literally fuse themselves to the female's body, becoming a permanent appendage that provides sperm whenever needed. The deep ocean is filled with these kinds of evolutionary solutions to the extreme challenges of life in the abyss. Creatures have evolved ways to survive that seem impossible by surface standards. Some deep-sea fish have transparent heads that allow them to see in multiple directions simultaneously. Others have expandable stomachs that can accommodate prey larger than themselves, essential in an environment where meals are rare and unpredictable. The Dumbo octopus, with its ear-like fins that flutter as it swims, represents one of the most charming inhabitants of the deep ocean. These creatures live at depths exceeding 4,000 meters, using their unique fins to propel themselves through the water with an almost ethereal grace. They're like underwater angels, floating through the darkness with a beauty that seems impossible in such a hostile environment. But perhaps the most unsettling aspect of these depths is how they challenge our basic understanding of what Earth is really like. We think of our planet as a world of continents and oceans, but the reality is that Earth is an ocean world with a few patches of dry land scattered on the surface. The vast majority of our planet's livable space exists in these crushing depths, in conditions so extreme that they make the harshest environments on land seem hospitable by comparison. The deep ocean represents the largest ecosystem on our planet, yet it remains almost completely unexplored. We've sent more people to space than to the deepest parts of our own oceans. The technology required to explore these depths is more complex and expensive than what we use to explore other planets. It's easier to send a robot to Mars than to send one to the bottom of the Mariana Trench. This means that right now, as you're reading this, there are entire mountain ranges, vast plains, and deep canyons on our own planet that no human has ever seen. There are species of creatures living in our oceans that are completely unknown to science, ecosystems that operate on principles we don't yet understand, and geological processes that could reshape our understanding of how planets work. The deep ocean isn't just unexplored, it's actively mysterious. Every expedition to these depths reveals phenomena that challenge our basic assumptions about life, geology, and chemistry. Scientists regularly discover new species that seem to violate the laws of biology, geological formations that shouldn't exist according to our current understanding, and chemical processes that open up entirely new fields of research. Recent discoveries have revealed underwater lakes at the bottom of the ocean, bodies of water so dense with dissolved minerals that they form distinct layers separate from the surrounding seawater. These brine pools create underwater shorelines, complete with beaches, where the dense brine meets the less dense seawater above. Fish can literally swim along the surface of these underwater lakes, creating scenes that look like something from an alien world. The deep ocean contains more water than all the rivers, lakes, and underground aquifers on Earth combined. Yet we know less about this vast underwater realm than we do about the surface of the moon. Every cubic meter of deep ocean water contains mysteries that could revolutionize our understanding of life itself. As we continue to develop better technology for exploring these depths, we're discovering that the deep ocean isn't just a remote, alien environment, it's intimately connected to every aspect of life on our planet. The deep ocean currents regulate our climate. The deep-sea ecosystems process vast amounts of carbon dioxide, and the creatures living in these depths may hold the keys to understanding how life itself began on Earth. The deep ocean represents the final frontier on our own planet, a vast underwater universe that remains as mysterious and unexplored as the surface of distant planets. And as we've seen in our journey through these crushing depths, it's a world that challenges everything we think we know about what's possible on Earth. The creatures we encounter at these impossible depths have evolved survival strategies that seem to mock the laws of physics as we understand them. Consider the barrel-eye fish, a transparent-headed wonder that lives in the crushing darkness of the mesopelagic zone. This ethereal creature has a completely see-through skull, allowing its tubular eyes to rotate upward inside its head to spot the silhouettes of prey against the faint light filtering down from above. It's like nature decided to create a living X-ray machine and set it loose in the abyss. But transparency isn't the only trick these deep-sea dwellers have mastered. The gulper eel has taken the concept of eating to absolute extremes. This nightmare creature can unhinge its massive jaw and expand its stomach to swallow prey several times larger than itself. In an environment where food is scarce and every meal might be your last, the ability to consume whatever crosses your path becomes essential for survival. The deeper we venture, the more the ocean reveals its capacity for hosting life forms that seem engineered by alien intelligence. At depths exceeding 3,000 meters, we encounter creatures that have evolved to exist without any connection whatsoever to the energy that powers the surface world. These organisms have created their own version of photosynthesis, but instead of using sunlight, they harness the chemical energy seeping from underwater volcanic vents. These hydrothermal vents represent oases of life in the deepest desert on our planet. Picture underwater geysers shooting superheated water rich in toxic chemicals, creating environments that should theoretically be uninhabitable. Yet around these vents, life flourishes in abundance that rivals tropical coral reefs. Giant tube worms, some reaching lengths of 8 feet, cluster around these chemical fountains like bizarre underwater flowers. What makes these tube worms truly alien is their complete lack of digestive systems. They have no mouth, no stomach, no intestines. Instead, they host colonies of bacteria within their bodies that convert the poisonous hydrogen sulfide from the vents into usable energy. It's a form of life so fundamentally different from everything we see on the surface that it forces us to reconsider what we even mean when we talk about living organisms. The thermal vents create underwater snowstorms of bacterial matter that drift through the water like living blizzards. This bacterial snow provides food for countless creatures that have never seen sunlight, creating food webs that operate on completely different principles than any ecosystem on the surface. It's like discovering that Earth has been harboring alien biospheres in its deepest places all along. But the thermal vents aren't the only source of life in these crushing depths. Cold seeps, where hydrocarbons and other chemicals leak slowly from the seafloor, create their own unique ecosystems. These cold seeps can support communities of life for hundreds or even thousands of years, creating underwater oases that persist across geological timescales. The creatures living around cold seeps have evolved into forms that seem pulled from science fiction. Clams the size of dinner plates filter chemicals from the water, while bacterial mats create underwater prairies that stretch for miles across the abyssal plains. These ecosystems operate so slowly that they seem frozen in time, with individual organisms living for centuries in the eternal twilight of the deep ocean. As we descend past 4,000 meters, we enter the abyssal zone proper, where the water pressure becomes so intense that it fundamentally alters the behavior of matter itself. At these depths, gases become compressed into liquid states, and the normal properties of water begin to change under the crushing force of miles of ocean pressing down from above. The abyssal plains, those vast underwater deserts that cover more area than all the continents combined, might appear empty at first glance. But look closer, and you'll discover that they're teeming with life forms so specialized for this environment that they couldn't survive anywhere else on Earth. Sea pigs, bizarre relatives of sea cucumbers, roam across the sea floor in herds like underwater cattle, feeding on the organic matter that drifts down from the world above. These abyssal plains are covered in a fine sediment made up of the remains of countless microscopic organisms that have been falling like snow for millions of years. This marine snow creates layers of organic matter that can be dozens of feet thick, forming underwater landscapes that record the history of ocean life, stretching back through geological ages. Buried within these sediment layers are the fossilized remains of creatures that lived and died in ancient oceans, creating a paleontological treasure trove that scientists are only beginning to explore. Every core sample taken from the abyssal seafloor reveals new insights into how life on Earth has evolved over millions of years, preserved in the crushing depths where decomposition occurs at a glacial pace. The pressure at these depths doesn't just affect living creatures, it creates geological phenomena that seem to defy logic. Underwater rivers of dense cold water flow along the ocean floor for thousands of miles, carrying sediment and nutrients across entire ocean basins. These deep ocean currents are so powerful that they can carve canyons in the seafloor, creating underwater landscapes that rival anything found on dry land. The Mediterranean outflow, water for example, flows from the Mediterranean Sea into the Atlantic Ocean, creating an underwater river that's denser and saltier than the surrounding seawater. This underwater river maintains its distinct identity for thousands of miles, flowing along the ocean floor like a liquid highway that connects different parts of the deep ocean ecosystem. But it's not just water that flows through these depths. Underwater avalanches, called turbidity currents, can carry massive amounts of sediment across the abyssal plains at speeds exceeding 60 miles per hour. These underwater landslides can bury entire ecosystems under layers of sediment, yet somehow life always finds a way to recover and adapt to the changing conditions. The geological activity at these depths creates features that dwarf anything found on the surface. Underwater mountain ranges stretch for thousands of miles along the mid-ocean ridges, where tectonic plates are slowly pulling apart and creating new oceanic crust. These underwater mountain ranges are home to some of the most extreme ecosystems on our planet, where life thrives in conditions that combine crushing pressure with volcanic heat. The Lost City hydrothermal field, located on the mid-Atlantic ridge, creates underwater towers of calcium carbonate that reach heights of over 18 stories. These towering spires, some over 60 meters tall, are formed by chemical reactions between seawater and the rocks of the ocean floor, creating structures that seem more like alien architecture than natural formations. Around these towering spires, life has evolved forms that seem impossible by any reasonable standard. Microorganisms live within the rock itself, feeding on chemical reactions that occur deep within the Earth's crust. These rock-eating bacteria create their own ecosystems within the solid stone, turning the boundary between living and non-living matter into something fluid and strange. The chemistry of water at these depths becomes increasingly exotic as we descend deeper. Dissolved gases reach concentrations that would be toxic at the surface, yet deep-sea organisms have evolved to not just tolerate, but require these chemical conditions for survival. Some deep-sea bacteria actually die when exposed to normal atmospheric conditions, essentially poisoned by the oxygen levels that surface life depends on. Methane hydrates, frozen deposits of methane trapped in ice-like structures, cover vast areas of the deep ocean floor. These deposits contain more energy than all known oil and gas reserves combined, yet they exist in a delicate balance that depends on the extreme pressure and cold temperatures of the deep ocean. Any change in these conditions could release massive amounts of methane into the atmosphere, potentially altering Earth's climate in ways we're only beginning to understand. The deep ocean acts as a massive carbon storage system, absorbing carbon dioxide from the atmosphere and transporting it to the deepest parts of the ocean through a process scientists call the biological pump. Marine organisms at the surface absorb carbon dioxide, and when they die, their remains sink to the ocean floor, effectively removing carbon from the atmospheric system for thousands of years. This deep ocean carbon storage system is so efficient that it regulates Earth's climate on geological timescales. The deep ocean contains 50 times more carbon than the atmosphere, stored in forms that range from dissolved carbon dioxide to the calcium carbonate shells of countless microscopic organisms that have been accumulating on the seafloor for millions of years. But the deep ocean's role in regulating our planet's climate goes beyond just storing carbon. The deep ocean currents that we've been following on our descent are part of a global circulation system that transports heat around the planet. Water that sinks in the polar regions carries cold, dense water to the deepest parts of the ocean, while warmer water rises to the surface in tropical regions, creating a global conveyor belt that helps regulate Earth's temperature. This thermohaline circulation, driven by differences in temperature and salinity, moves water through the deep ocean at speeds that make continental drift seem rapid by comparison. A molecule of water that sinks to the deep ocean in the North Atlantic might not return to the surface for over 1,000 years, spending centuries travelling through the crushing darkness of the abyss before eventually rising in the Pacific Ocean. The deep ocean currents create underwater weather systems that operate on timescales completely different from anything we experience on the surface. Deep ocean storms, driven by temperature and salinity differences, can create underwater cyclones that persist for months or even years. These deep ocean storms transport nutrients and organisms across vast distances, creating connections between ecosystems that are separated by thousands of miles. The Labrador seawater, formed in the North Atlantic, sinks to depths of over 2,000 meters and flows southward along the western edge of the Atlantic basin. This deep water mass maintains its distinct temperature and chemical signature for thousands of miles, creating an underwater river that connects the Arctic Ocean to the equatorial Atlantic. As this deep water travels through the abyss, it carries with it a cargo of dissolved nutrients that eventually upwells in other parts of the ocean, bringing deep ocean chemistry to surface ecosystems. This global circulation system means that nutrients from the deepest parts of our ocean eventually reach surface waters, connecting the alien world of the abyss to the familiar ecosystems we see at the surface. The Antarctic bottom water represents the densest water mass in the world's oceans, formed in the frigid waters around Antarctica, where sea ice formation leaves behind water so cold and salty that it sinks to the very bottom of the ocean basins. This water mass flows northward along the ocean floor, filling the deepest parts of the Atlantic, Pacific, and Indian Oceans with water that originated in the polar regions. The journey of Antarctic bottom water from its formation around Antarctica to its eventual mixing with other water masses can take over 1,000 years. During this time, this water mass travels through some of the most extreme environments on our planet, carrying with it chemical signatures that scientists use to trace the movement of water through the global ocean system. The deep ocean's role as a global mixing chamber becomes even more apparent when we consider how it processes the chemical output of human civilization. Carbon dioxide from fossil fuel burning doesn't just stay in the atmosphere. Much of it eventually dissolves into seawater and is transported to the deep ocean through the same biological and physical processes that have been operating for millions of years. But the deep ocean's capacity to absorb carbon dioxide isn't unlimited. As atmospheric carbon dioxide levels continue to rise, the ocean becomes more acidic, creating conditions that can dissolve the calcium carbonate shells and skeletons of marine organisms. This ocean acidification affects organisms throughout the water column, from surface plankton to deep-sea corals that have been growing in the abyss for thousands of years. The deep-sea corals, those ancient organisms that create underwater forests in complete darkness, are particularly vulnerable to ocean acidification. These corals, some of which have been growing for over 4,000 years, create complex three-dimensional structures that provide habitat for countless deep-sea organisms. They're like underwater redwood forests, creating biodiversity hotspots in the crushing darkness of the abyss. Some deep-sea coral reefs are larger than cities, creating underwater landscapes that support thousands of species found nowhere else on Earth. The Lophelia reefs off the coast of Norway stretch for miles along the continental shelf, creating underwater mountains made entirely of coral that have been growing for millennia in the eternal darkness of the deep ocean. These deep-sea coral reefs operate on biological timescales that make tropical coral reefs seem ephemeral by comparison. While tropical corals can grow several inches per year, deep-sea corals grow at rates measured in millimeters per decade. The largest deep-sea coral structures represent thousands of years of continuous growth, creating biological monuments that have been accumulating calcium carbonate since before human civilization began. The creatures that inhabit these deep-sea coral reefs have evolved into forms that seem designed for an alien world. Deep-sea basket stars, relatives of starfish, with arms that can reach spans of several feet, perch on coral branches like underwater trees, filtering plankton from the water with their intricate branching arms. These creatures can live for decades in the same location, slowly growing larger as they filter nutrients from the deep ocean currents. The deep-sea sponge gardens that grow alongside these coral reefs create underwater cities that can be seen from space-based sonar systems. Some of these sponge reefs cover areas larger than entire countries, creating three-dimensional habitats that extend hundreds of feet above the seafloor. The glass sponge reefs off the coast of British Columbia were thought to be extinct until they were rediscovered in the 1980s, revealing underwater ecosystems that had been thriving in secret for thousands of years. These glass sponges, with their intricate silica skeletons that look like spun glass, create structures so delicate they seem impossible in the crushing environment of the deep ocean. Yet these fragile-looking organisms are incredibly tough, able to withstand currents and pressures that would destroy most surface organisms. They filter vast amounts of water through their bodies, processing nutrients and chemicals in ways that help regulate the chemistry of the deep ocean. The deep ocean's biological diversity becomes even more staggering when we consider the microbial life that exists in the sediments of the abyssal seafloor. These sediments, in some places over a mile thick, contain more living biomass than all terrestrial ecosystems combined. The bacteria and archaea living in these sediments exist in a state of near-suspended animation, with metabolic rates so slow that individual cells might divide only once every 1,000 years. These sediment-dwelling microorganisms represent some of the oldest continuous ecosystems on our planet. Some deep-sea sediments contain microbial communities that have been essentially unchanged for millions of years, creating biological time capsules that preserve ancient forms of life in the crushing depths of the ocean floor. The discovery of life in deep ocean sediments has revolutionized our understanding of the limits of life on Earth. Scientists have found living microorganisms in sediments that are over 2 million years old, buried under thousands of feet of accumulated marine sediment. These ancient microbes exist in conditions of extreme pressure, near freezing temperatures, and complete darkness, yet they continue to maintain active metabolisms after millions of years of burial. The energy sources that support these buried ecosystems come from chemical reactions that occur within the sediments themselves. As organic matter decomposes over geological timescales, it creates a complex chemistry that can support microbial life for millions of years. These sediment ecosystems operate so slowly that they seem frozen in time, yet they process vast amounts of carbon and other nutrients over geological timescales. The deep ocean sediments also serve as a vast library of Earth's climate history. Each layer of sediment contains chemical signatures that record the conditions of ancient oceans, creating a detailed record of how our planet's climate has changed over millions of years. Ice core samples from glaciers can tell us about climate conditions going back hundreds of thousands of years, but deep ocean sediments preserve climate records stretching back over 100 million years. Within these sediment layers, scientists have discovered evidence of ancient catastrophes that reshaped life on Earth. The sediment layer that marks the extinction of the dinosaurs 66 million years ago can be found in deep ocean cores around the world, preserved as a thin layer rich in iridium and other elements that fell from space when an asteroid impact changed the course of evolution on our planet. The deep ocean sediments also preserve evidence of volcanic supereruptions, massive climate changes, and other events that have shaped the history of life on Earth. Each core sample taken from the deep ocean floor is like opening a book that tells the story of our planet's past, written in the language of chemistry and preserved in the crushing depths of the abyss. But perhaps the most remarkable aspect of these deep ocean sediments is how they continue to influence our planet's future. The chemical reactions occurring within these buried ecosystems help regulate the long-term chemistry of seawater, buffering changes in ocean acidity and helping to maintain the chemical conditions that support life throughout the ocean system. The deep ocean represents a vast reservoir of chemical stability that helps keep our planet's climate system in balance. The slow mixing of deep ocean water with surface water helps regulate atmospheric carbon dioxide levels over geological timescales, creating a planetary thermostat that has helped maintain habitable conditions on Earth for billions of years. As we approach the deepest parts of our journey, the Hadal Zone beckons with mysteries that challenge everything we think we know about the limits of life on Earth. This deepest realm of our ocean, named after the ancient Greek underworld, represents less than 1% of the ocean's volume, yet may contain some of the most extraordinary life forms on our planet. The trenches that define the Hadal Zone are not just deep, they're geologically active scars in the Earth's crust where tectonic plates collide with forces that can trigger earthquakes and volcanic eruptions. These trenches are constantly changing, with sediment slides and tectonic activity creating an environment that's both stable and chaotic, ancient and constantly renewed. The Mariana Trench, our final destination, represents not just the deepest point in our oceans, but potentially one of the most isolated ecosystems on our planet. The creatures living in Challenger Deep have been separated from the rest of the ocean's life forms for millions of years, evolving in complete isolation in conditions so extreme that they represent the absolute limits of what life can endure on our planet. Recent expeditions to these ultimate depths have revealed that even at the very bottom of our oceans, life persists in forms that continue to surprise and challenge our understanding of biology. The deepest fish ever recorded, a type of snailfish discovered at depths exceeding 8,000 meters, seems to dissolve the moment it's brought to the surface. Its body adapted so completely to extreme pressure that it cannot exist in any other environment. The Hadal Zone represents the final frontier of life on our planet, a realm so extreme and alien that exploring it requires technology more advanced than what we use to explore other worlds. Yet it's here, in the crushing darkness, at the very bottom of our oceans, that we may find clues to understanding how life began on Earth, and perhaps how it might exist on other worlds throughout the universe. As we prepare to make our final descent into Challenger Deep, we're about to enter a realm that fewer humans have visited than have walked on the surface of the moon. It's a place where the normal rules of biology and physics are pushed to their absolute breaking point, where life exists in forms so alien that they expand our understanding of what's possible in the universe. The journey to these ultimate depths isn't just about reaching the bottom of our oceans, it's about discovering that our planet still holds mysteries as profound and alien as anything we might find among the stars. In the crushing darkness of the deepest ocean, we find not just the limits of our world, but the limitless capacity of life to adapt, survive, and thrive in conditions that challenge everything we thought we knew about what it means to be alive on planet Earth. The pressure at these ultimate depths defies human comprehension. We're talking about forces so extreme that they would compress a steel submarine into a ball the size of a marble in the blink of an eye. The water itself becomes something almost alien under these conditions, denser and heavier than anything we experience at the surface. At 11,000 meters below sea level, we've traveled deeper than commercial aircraft fly high. The pressure here exceeds 1,000 times what we feel at sea level. It's like having the weight of 50 jumbo jets pressing down on every square inch of your body. No human could survive even a fraction of a second at these depths, without protection that makes spacesuits look primitive by comparison. Yet even here, at the very edge of what our planet can offer, life finds a way to persist. The creatures that call these ultimate depths home have evolved beyond anything we might recognize as earthly life. They exist in a realm of perpetual night, where temperatures hover just above freezing and the pressure would instantly crush any organism adapted to surface conditions. These are not just deep-sea creatures, they're the ultimate survivors, living proof that life can adapt to conditions that seem impossible. The deepest dwelling fish ever discovered, found at depths exceeding 8,000 meters, represents a triumph of evolutionary adaptation. These ghostly creatures, with their transparent bodies and gel-like consistency, seem more like living liquid than solid organisms. Their bones have been replaced by cartilage, their gas-filled swim bladders eliminated entirely, and their bodies composed largely of water and specialized proteins that maintain their structure under crushing pressure. These fish move through the water like phantoms, their movements slow and deliberate in the thick, pressure-dense environment of the deep Hadal zone. They feed on the sparse organic matter that manages to drift down from the world above, competing for resources in an environment where every scrap of nutrition represents a victory against the crushing forces of the abyss. But fish are not the only inhabitants of these extreme depths. Amphipods, tiny shrimp-like creatures, have been discovered thriving at depths that were once thought impossible for complex life. These remarkable organisms, no larger than your thumb, have evolved into living pressure vessels, their bodies specially adapted to exist under forces that would destroy virtually any other form of life. The Hadal amphipods represent one of the most successful adaptations to extreme environments on our planet. They scavenge along the bottom of the deepest trenches, feeding on whatever organic matter manages to complete the long journey from the surface world. Their bodies are transparent, allowing them to remain nearly invisible in the eternal darkness of the deep ocean. What makes these creatures even more remarkable is their ability to reproduce and thrive in conditions that would be instantly fatal to their surface-dwelling relatives. They've evolved specialized enzymes that function under extreme pressure, cellular structures that can withstand crushing forces, and metabolic processes that operate efficiently in the near-freezing temperatures of the abyss. The microbial life at these depths pushes the boundaries of what we consider possible for living organisms. Bacteria and archaea exist in the sediments of the deepest trenches, living in conditions that combine extreme pressure with chemical environments that would be toxic to most life forms. These microorganisms have evolved to not just tolerate, but require the extreme conditions of the Hadal zone. Some of these deep trench microbes derive their energy from chemical reactions that occur within the sediments themselves. They feed on compounds that seep from the Earth's crust, creating ecosystems that are completely independent of sunlight and the surface world. These bacterial communities can exist for thousands of years in the same location, slowly processing chemicals and organic matter in the eternal darkness of the deepest ocean. The discovery of thriving microbial communities in the deepest parts of our oceans has revolutionized our understanding of life's limits. These organisms exist in conditions that closely resemble what we might find on other worlds, making them invaluable for understanding how life might exist beyond Earth. They represent living examples of how life can adapt to the most extreme environments our planet has to offer. The geological processes at these depths create landscapes that seem pulled from alien worlds. The deepest trenches are not static features, but dynamic systems where tectonic forces constantly reshape the seafloor. Earthquakes regularly shake these depths, creating underwater avalanches that can bury entire ecosystems under tons of sediment. Yet life persists through these catastrophic events. The organisms living in the Hadal zone have evolved strategies for surviving the geological violence that characterizes these depths. Some can burrow deep into sediments to avoid being swept away, while others have developed the ability to quickly recolonize areas that have been disturbed by seismic activity. The Challenger Deep itself represents the ultimate expression of our planet's geological forces. This narrow slot in the Earth's crust, barely wide enough to fit a city block, plunges to depths that exceed the height of Mount Everest. The sides of this underwater canyon are so steep that they create their own unique ecosystems, with different communities of organisms adapted to life at different depths within the trench. The water chemistry at Challenger Deep is unlike anything found elsewhere on our planet. The extreme pressure creates conditions where dissolved gases behave in unusual ways, and the isolation of the deepest water from the rest of the ocean creates a unique chemical environment. This water has been cut off from the surface world for thousands of years, creating a chemical time capsule that preserves ancient ocean conditions. Recent explorations of Challenger Deep have revealed features that challenge our understanding of deep-sea geology. Underwater hot springs, driven by geothermal activity deep within the Earth's crust, create oases of warmth in the crushing cold of the deepest ocean. These thermal features support their own unique ecosystems, with organisms that have evolved to thrive in the unusual conditions created by the interaction of extreme pressure and geothermal heat. The sediments at the bottom of Challenger Deep contain a record of Earth's history that stretches back millions of years. Each layer tells a story of ancient climates, volcanic eruptions, and extinction events that have shaped our planet's evolution. Scientists studying these sediments have discovered evidence of massive underwater landslides, tsunami deposits, and other catastrophic events that have occurred in the deepest parts of our oceans. But perhaps the most remarkable discovery in these ultimate depths is the presence of human-made objects. Plastic debris, carried by deep ocean currents, has been found even in the deepest parts of the Mariana Trench. This sobering discovery reveals that human influence has reached even the most remote and extreme environments on our planet. The presence of plastic pollution in Challenger Deep represents a stark reminder of how interconnected our planet's systems really are. Materials discarded at the surface can eventually find their way to the deepest parts of our oceans, carried by the same currents and processes that transport nutrients and organisms throughout the global ocean system. Yet even in the face of human impact, life in the deepest ocean continues to surprise us with its resilience and adaptability. Microorganisms have been discovered that can actually break down plastic polymers, potentially offering solutions to one of our most pressing environmental challenges. These plastic-eating bacteria, evolved in the crushing depths of the ocean, represent nature's own attempt to adapt to the changes humans have brought to our planet. The exploration of these deepest depths requires technology that pushes the absolute limits of human engineering. The submersibles capable of reaching Challenger Deep must be constructed from materials that can withstand pressures equivalent to having several aircraft carriers stacked on top of them. The viewing windows alone require engineering solutions that border on the impossible, using materials and techniques that didn't exist just decades ago. The psychological challenges of descending to these depths are as extreme as the physical ones. The journey to the bottom of Challenger Deep takes hours, during which explorers must cope with the knowledge that they are traveling to a place more isolated and hostile than the surface of the moon. The darkness outside the submersible is absolute, broken only by the artificial lights of the vessel itself. The sense of isolation at these depths is profound. Radio communication with the surface is impossible, and the explorers are truly alone in one of the most extreme environments on our planet. The weight of miles of water pressing down from above creates a psychological pressure that can be as crushing as the physical forces surrounding the vessel. Yet those who have made this ultimate journey describe it as a transformative experience. To witness firsthand the alien landscapes of the deepest ocean, to see creatures that exist nowhere else in the universe, to touch the very bottom of our planet's most extreme environment, is to gain a perspective on Earth that few humans will ever experience. The scientific discoveries made during these deep-sea expeditions continue to revolutionize our understanding of life on Earth. Each dive to the deepest parts of our oceans reveals new species, new geological features, and new insights into how life can adapt to the most extreme conditions imaginable. These discoveries don't just expand our knowledge of our own planet, they inform our understanding of how life might exist throughout the universe. The extreme conditions found in the deepest parts of our oceans closely resemble those that might exist on other worlds. The high pressure, low temperature, and chemical environments of the Hadal Zone provide analogues for conditions we might find on moons like Europa or Enceladus, where subsurface oceans exist beneath miles of ice. The organisms that thrive in these extreme earthly environments offer clues about what life might look like elsewhere in the cosmos. As we continue to explore these deepest realms, we're discovering that the boundaries between geology and biology become increasingly blurred. The extreme conditions of the deep ocean create environments where living and non-living processes interact in ways that challenge our basic understanding of how planets work. The deep ocean represents not just the limits of life on Earth, but the frontier where life and planet merge into something greater than either could achieve alone. The future of deep-sea exploration promises even more remarkable discoveries. New technologies are being developed that will allow us to explore these depths more thoroughly and with greater safety. Autonomous underwater vehicles, equipped with advanced sensors and sampling equipment, are beginning to reveal the secrets of the deepest ocean in ways that were impossible just years ago. These robotic explorers can spend months in the deepest parts of our oceans, collecting data and samples that would be impossible for human explorers to obtain. They're revealing that the deep ocean is far more dynamic and active than we ever imagined, with geological processes, biological communities, and chemical reactions that operate on scales both vast and intimate. The deep ocean currents that we've followed on our journey don't just transport water, they carry with them the chemical signatures of the deepest parts of our planet. These currents eventually return to the surface, bringing with them nutrients and chemicals that have been processed in the extreme conditions of the abyss. The deep ocean thus influences surface ecosystems in ways we're only beginning to understand. The carbon cycle that operates in the deep ocean plays a crucial role in regulating Earth's climate over geological timescales. The creatures living in the deepest parts of our oceans are part of a vast biological pump that moves carbon from the atmosphere to the deep ocean, where it can be stored for thousands of years. Understanding these deep-sea processes is crucial for predicting how our planet's climate system will respond to ongoing changes. The deep ocean also serves as a vast reservoir of biodiversity, containing species and ecosystems that exist nowhere else on Earth. As we continue to explore these depths, we're discovering that the deep ocean may contain more species diversity than all terrestrial ecosystems combined. Most of these species remain completely unknown to science, representing a vast frontier of biological discovery. The pharmaceutical potential of deep-sea organisms is only beginning to be explored. The extreme conditions of the deep ocean have driven the evolution of biochemical compounds that have no equivalents in surface-dwelling organisms. These unique biomolecules could lead to new medicines, materials, and technologies that could revolutionize human society. But perhaps the most profound impact of deep-sea exploration is how it changes our perspective on our own planet. The deep ocean represents the largest living space on Earth, yet it remains almost completely unexplored. We are inhabitants of an ocean planet, yet we know more about the surfaces of other worlds than we do about the depths of our own. The journey through the deepest parts of our oceans reveals that Earth is far stranger, more alien, and more wonderful than most of us ever imagined. The creatures living in these crushing depths, the geological processes that shape the deepest seafloor, and the chemical reactions that occur in the most extreme environments on our planet all combine to create a world that challenges our basic assumptions about what life can achieve. As we've descended through the layers of our ocean, from the familiar surface waters to the alien realm of the Hadal Zone, we've witnessed the incredible diversity of life that exists on our planet. We've seen how life adapts to conditions that seem impossible, how it thrives in environments that would be instantly fatal to surface dwellers, and how it continues to surprise us with its resilience and creativity. The deep ocean represents both the final frontier on our own planet and a window into the possibilities for life throughout the universe. In the crushing darkness of the deepest trenches, we find not just the limits of our world, but evidence of life's unlimited capacity to adapt, survive, and flourish in conditions that expand our understanding of what it means to be alive. The mysteries of the deep ocean continue to call to us, promising discoveries that will reshape our understanding of our planet and our place in the cosmos. Each expedition to these depths reveals new wonders, new challenges, and new possibilities for life in the universe. The deep ocean remains our planet's greatest frontier, a realm of endless mystery and boundless potential for discovery. In the end, our journey through the depths of the ocean reveals that we live on a planet that is far more extraordinary than we ever imagined. The crushing depths that we've explored represent not just the physical limits of our world, but the unlimited possibilities for life to adapt, thrive, and surprise us with its endless creativity and resilience. The ocean's deepest places remind us that our planet still holds secrets as profound and alien as anything we might find among the stars. In the crushing darkness of the abyss, we discover that the greatest frontier for exploration and discovery lies not in the vastness of space, but in the crushing depths of our own world's oceans. The vastness of these crushing depths becomes even more staggering when you realize that we've only just begun to scratch the surface of what lies beneath. The technology required to explore these ultimate depths pushes every boundary of human engineering. Yet each expedition reveals that we're still missing enormous pieces of the puzzle. Consider the sheer scale of what remains unexplored. The Hadal Zone, those depths below 6,000 meters, covers an area roughly equivalent to the size of Australia. Yet we've explored less than 1% of it. Entire mountain ranges could exist down there, canyons that dwarf the Grand Canyon, and ecosystems more complex than anything we've discovered on land. And we would have absolutely no idea they're there. The creatures we've managed to discover in these depths represent just a tiny fraction of what actually exists. Marine biologists estimate that for every species we've identified in the deep ocean, there are probably dozens more that remain completely unknown to science. We're talking about a hidden biosphere that could contain millions of species that have never been seen by human eyes. What makes this even more remarkable is that these aren't just small, simple organisms hiding in the depths. Recent discoveries have revealed complex ecosystems operating at depths that were once thought to be biological deserts. The deeper we look, the more we realize that the ocean floor is alive with activity that operates on scales both microscopic and massive. The bioluminescent displays in these depths create light shows that would put any fireworks display to shame. Creatures generate their own light through chemical reactions, creating cascades of blue, green, and red that pulse through the darkness like living fireworks. Some of these displays can be seen from submersibles miles away, creating underwater aurora that dance through the eternal night of the deep ocean. But it's not just the beauty of these depths that captures the imagination. The practical implications of what we're discovering down there could revolutionize our understanding of life itself. The enzymes that allow deep-sea creatures to function under extreme pressure are already being studied for potential applications in medicine and industry. These biological machines, evolved over millions of years in the crushing depths, could lead to breakthroughs in everything from drug delivery to materials science. The extreme conditions of the deep ocean have forced life to develop solutions that seem to violate the basic principles of biology as we understand them. Some deep-sea bacteria can actually repair their DNA faster than the crushing pressure can damage it, creating a biological arms race between environmental stress and cellular repair mechanisms that has been going on for millions of years. The chemical processes occurring in these depths are equally mind-bending. The intense pressure creates conditions where normal chemical reactions behave in completely unexpected ways. Water itself becomes a different substance under these conditions, with properties that can only be studied in laboratory conditions that simulate the extreme environment of the deep ocean. Recent studies have revealed that the deep ocean contains vast deposits of rare earth elements that are crucial for modern technology. These mineral deposits, formed over millions of years by geological processes that occur only in the deepest parts of our oceans, could represent the future of resource extraction on our planet. However, the environmental cost of mining these depths could be catastrophic for ecosystems that have remained undisturbed for millions of years. The deep ocean currents that flow through these depths don't just move water, they transport heat, nutrients, and chemical signatures that influence weather patterns across the entire planet. A change in deep ocean circulation could alter climate patterns in ways that would affect every ecosystem on Earth. The deep ocean represents a vast engine that helps regulate our planet's climate. Yet we understand its workings about as well as we understand the internal mechanisms of a distant star. The sediments that cover the deepest parts of our ocean floor contain a record of Earth's history that stretches back hundreds of millions of years. Each layer tells a story of ancient climates, massive volcanic eruptions, and extinction events that have shaped the evolution of life on our planet. Scientists studying these sediment cores have discovered evidence of asteroid impacts, supervolcanic eruptions, and climate changes that dwarf anything in recorded human history. But perhaps the most unsettling discovery in these depths is evidence of how quickly things can change. The deep ocean, which we think of as stable and unchanging, actually experiences catastrophic events that can reshape entire ecosystems in a matter of hours. Underwater landslides can move billions of tons of sediment across vast distances, burying ancient ecosystems and creating new ones in their wake. The creatures living in these depths have evolved strategies for surviving these catastrophic events that seem almost supernatural. Some can enter states of suspended animation that allow them to survive being buried under tons of sediment for years at a time. Others have developed the ability to rapidly migrate vertically through the water column, escaping disaster by moving to different depth zones when conditions become unfavorable. The pressure at these depths doesn't just crush objects, it fundamentally alters the behavior of sound, light, and even time itself. Sound waves travel differently through pressure-dense water, creating acoustic environments that are completely alien to anything we experience on the surface. Some deep-sea creatures have evolved to use these acoustic properties for communication, creating sound-based ecosystems that operate on principles we're only beginning to understand. The darkness of these depths isn't just an absence of light, it's a presence unto itself. The complete blackness creates sensory conditions that can drive surface-dwelling creatures to madness. Yet the organisms that call these depths home have evolved senses that we can barely comprehend. Some can detect chemical gradients so subtle that they can navigate by taste alone, while others have developed electrical senses that allow them to detect the bioelectric fields generated by other living creatures. The food webs that operate in these depths function on principles that seem to defy the basic laws of ecology. In a world where photosynthesis is impossible, creatures have evolved to extract energy from sources that would be toxic to surface life. Entire ecosystems operate on the chemical energy released by underwater volcanic activity, creating biological communities that are completely independent of the sun. The reproductive strategies of deep-sea creatures are as alien as their feeding habits. Some species have evolved to reproduce only once every several decades, timing their reproduction with rare environmental events that might occur only a few times in a human lifetime. Others have developed the ability to reproduce asexually, creating genetic clones that can survive in isolation for centuries. The migration patterns of deep-sea creatures create vertical highways that connect different layers of the ocean in ways that surface dwellers never experience. Some creatures spend their entire lives traveling between different depth zones, following food sources and temperature gradients in journeys that can span thousands of vertical feet. These migrations create connections between ecosystems that exist at different depths, linking the familiar surface world with the alien realm of the abyss. The bacterial communities that exist in the deepest sediments represent some of the oldest continuous ecosystems on our planet. These microbial societies have been operating in the same locations for millions of years, slowly processing organic matter and chemicals in cycles that operate on geological timescales. Individual bacteria in these communities might divide only once every 1,000 years, creating biological processes that unfold over timeframes that make human civilization seem like a brief moment. The chemical signatures preserved in these deep sediments provide a record of how Earth's oceans have changed over millions of years. Scientists studying these chemical records have discovered evidence of massive changes in ocean chemistry that occurred during major extinction events, providing clues about how life on Earth has responded to catastrophic changes in the past. The deep ocean's role in regulating Earth's climate becomes even more apparent when we consider the vast amount of carbon stored in these depths. The organic matter that accumulates in deep ocean sediments represents one of the largest carbon reservoirs on our planet, storing carbon that has been removed from the atmospheric system for millions of years. This deep ocean carbon storage system helps regulate atmospheric carbon dioxide levels over geological timescales, creating a planetary thermostat that has helped maintain habitable conditions on Earth for billions of years. But this system isn't static. Changes in deep ocean circulation, temperature, or chemistry could release vast amounts of stored carbon back into the atmosphere, potentially triggering climate changes that would dwarf anything in human experience. The deep ocean represents both a stabilizing force for Earth's climate and a potential source of catastrophic change, depending on how human activities affect these ancient systems. The exploration of these depths requires not just advanced technology, but also a fundamental shift in how we think about our planet. The familiar world of continents and surface oceans represents just a thin skin on a planet that is dominated by the alien realm of the deep ocean. We are inhabitants of an ocean world, yet most of us live our entire lives without ever considering the vast underwater universe that exists beneath our feet. The psychological impact of exploring these depths cannot be overstated. Those who have descended to the deepest parts of our oceans describe a sense of awe and humility that comes from witnessing firsthand the alien landscapes of the abyss. The experience of being surrounded by crushing darkness, knowing that you are farther from the surface than Mount Everest is tall, creates a perspective on Earth that few humans will ever experience. The isolation experienced at these depths is profound. Communication with the surface is impossible, and explorers are truly alone in one of the most extreme environments on our planet. The silence of the deep ocean is broken only by the sounds of the exploration vessel itself, creating an acoustic environment that is both peaceful and terrifying. Yet those who have made this ultimate journey describe it as transformative. To witness the alien beauty of the deepest ocean, to see creatures that exist nowhere else in the universe, to touch the very bottom of our planet's most extreme environment, is to gain an understanding of Earth that changes how you see everything else. The scientific discoveries made during these expeditions continue to challenge our basic assumptions about life, geology, and chemistry. Each dive to the deepest parts of our oceans reveals new species that seem to violate the laws of biology, geological formations that shouldn't exist according to our current understanding, and chemical processes that open up entirely new fields of research. The creatures discovered in these depths don't just expand our catalogue of Earth's biodiversity, they fundamentally challenge our understanding of what life can achieve. The pressure-resistant proteins found in deep-sea organisms are being studied for potential applications in medicine and biotechnology. The unique metabolic pathways that allow these creatures to survive in extreme conditions could lead to breakthroughs in everything from antibiotic development to sustainable energy production. The geological processes occurring at these depths are equally revolutionary. The discovery of active volcanic systems in the deepest parts of our oceans has revealed that our planet is far more geologically active than we ever imagined. These deep-sea volcanic systems don't just create new seafloor, they generate unique mineral deposits and create chemical environments that support forms of life found nowhere else on Earth. The hydrothermal vents that dot the deepest parts of our oceans represent oases of life in what was once thought to be a biological desert. These underwater geysers, shooting superheated water rich in minerals and chemicals, create environments that support ecosystems rivaling tropical rainforests in their complexity and diversity. The chemistry of these hydrothermal systems is so extreme that it challenges our basic understanding of how life can function. The water around these vents can reach temperatures that would instantly kill most surface organisms. Yet entire communities of life thrive in these conditions. The organisms living around these vents have evolved biochemical processes that seem to violate the basic principles of biology as we understand them. The discovery of these hydrothermal vent ecosystems has revolutionized our understanding of how life might exist elsewhere in the universe. The extreme conditions found around these vents closely resemble those that might exist on other worlds, particularly the subsurface oceans of moons like Europa and Enceladus. The organisms that thrive in these earthly extreme environments provide templates for what life might look like elsewhere in the cosmos. The deep ocean represents not just the final frontier on our own planet, but a laboratory for understanding the possibilities for life throughout the universe. The extreme conditions found in the deepest parts of our oceans push the boundaries of what we thought was possible for living organisms, expanding our understanding of the conditions under which life can exist. As we continue to explore these depths, we're discovering that the boundaries between what we consider living and non-living become increasingly blurred. The extreme conditions of the deep ocean create environments where geological and biological processes interact in ways that challenge our basic understanding of how planets work. The future of deep-sea exploration promises discoveries that will continue to reshape our understanding of our planet and our place in the cosmos. New technologies are being developed that will allow us to explore these depths more thoroughly and safely than ever before. Autonomous underwater vehicles, equipped with advanced sensors and sampling equipment, are beginning to reveal the secrets of the deepest ocean in ways that were impossible just years ago. These robotic explorers can spend months in the deepest parts of our oceans, operating in conditions that would be instantly fatal to human explorers. They're revealing that the deep ocean is far more dynamic and active than we ever imagined, with geological processes, biological communities, and chemical reactions that operate on scales both vast and intimate. The data collected by these automated systems is revealing that the deep ocean plays a far more important role in regulating Earth's climate and supporting global ecosystems than we ever realized. The deep ocean currents that we've followed on our journey don't just transport water, they carry with them the chemical signatures of the entire planet, creating connections between the deepest parts of our oceans and the most familiar surface environments. The carbon cycle that operates in the deep ocean is crucial for understanding how our planet's climate system will respond to ongoing changes. The creatures living in the deepest parts of our oceans are part of a vast biological pump that moves carbon from the atmosphere to the deep ocean, where it can be stored for thousands of years. Understanding these deep-sea processes is essential for predicting how our planet will respond to the changes we're making to the atmospheric system. The deep ocean also serves as a vast reservoir of biodiversity that we're only beginning to explore. The species living in these depths represent evolutionary lineages that have been isolated for millions of years, creating unique forms of life that exist nowhere else on Earth. Many of these species remain completely unknown to science, representing a vast frontier of biological discovery that could take centuries to fully explore. The pharmaceutical potential of deep-sea organisms is staggering. The extreme conditions of the deep ocean have driven the evolution of biochemical compounds that have no equivalents anywhere else on Earth. These unique biomolecules could lead to new medicines, materials, and technologies that could revolutionize human society in ways we can barely imagine. But perhaps the most profound impact of deep-sea exploration is how it changes our perspective on our own planet. The deep ocean represents the largest living space on Earth, yet it remains almost completely unexplored. We are inhabitants of an ocean planet, yet most of us live our entire lives without ever considering the vast underwater universe that exists beneath the familiar surface world. The journey through the deepest parts of our oceans reveals that Earth is far stranger, more alien, and more wonderful than most of us ever imagined. The creatures living in these crushing depths, the geological processes that shape the deepest seafloor, and the chemical reactions that occur in the most extreme environments on our planet all combine to create a world that challenges our basic assumptions about what life can achieve. As we've descended through the layers of our ocean, from the familiar surface waters to the alien realm of the Hadal Zone, we've witnessed the incredible diversity and resilience of life on our planet. We've seen how life adapts to conditions that seem impossible, how it thrives in environments that would be instantly fatal to surface dwellers, and how it continues to surprise us with its creativity and determination. The deep ocean represents both the final frontier on our own planet and a window into the possibilities for life throughout the universe. In the crushing darkness of the deepest trenches, we find not just the limits of our world, but evidence of life's unlimited capacity to adapt, survive, and flourish in conditions that expand our understanding of what it means to be alive. The mysteries of the deep ocean continue to call to us, promising discoveries that will reshape our understanding of our planet and our place in the cosmos. Each expedition to these depths reveals new wonders, new challenges, and new possibilities for life in the universe. The deep ocean remains our planet's greatest frontier, a realm of endless mystery and boundless potential for discovery. In these crushing depths, we discover that the greatest adventures aren't found in the vastness of space, but in the alien realm that exists right here on our own planet. The deep ocean reminds us that Earth still holds secrets as profound and mysterious as anything we might find among the stars, waiting in the crushing darkness for brave explorers to uncover them. The geological violence that shapes these ultimate depths is beyond anything we witness on the surface. Imagine earthquakes so powerful they can move entire underwater mountain ranges, creating avalanches of sediment that flow across the ocean floor like liquid concrete. These underwater landslides can travel for hundreds of miles, carrying with them the accumulated remains of millions of years of marine life. The trenches themselves are not static features carved into the seafloor. They're dynamic, living scars in the Earth's crust where massive tectonic plates collide with forces that make surface earthquakes seem gentle by comparison. The Mariana Trench is constantly changing, with new sections opening up while others collapse under the immense geological pressures. At these depths, the very concept of solid ground becomes questionable. The sediment layers that cover the trench floors can be hundreds of feet thick, composed of the compressed remains of countless microscopic organisms that have been settling like snow for millions of years. Walking on this seafloor would be like walking on compressed history, each step crushing through layers that record the entire story of life in our oceans. The water at Challenger Deep has been trapped at these depths for thousands of years, cut off from the rest of the ocean by the unique geography of the trench. This ancient water has developed its own chemical signature, different from any other water on our planet. It's like discovering a liquid time capsule that preserves the chemistry of ancient oceans. The pressure at these ultimate depths creates phenomena that seem to mock the laws of physics. Gases that would normally bubble to the surface become trapped in liquid form, creating underwater rivers of liquid carbon dioxide that flow along the trench floor like ghostly streams. These chemical rivers support their own unique ecosystems, with organisms that have evolved to breathe liquid gas instead of dissolved oxygen. The temperature gradients in these trenches create their own weather systems. Hot water from geothermal vents mixes with the near-freezing water of the deep ocean, creating underwater storms that can persist for months. These thermal hurricanes transport nutrients and organisms across vast distances, connecting isolated ecosystems in ways that surface dwellers never experience. Recent discoveries have revealed that some trenches contain underwater lakes of brine so dense that submarines can actually float on their surface. These hypersaline pools, formed by the dissolution of ancient salt deposits, create distinct boundaries between different water masses. Fish literally swim along the shores of these underwater lakes, creating scenes that seem pulled from an alien world. The acoustic environment of these depths is equally bizarre. Sound waves travel differently through the pressure-dense water, creating acoustic shadows and echo chambers that can trap sounds for hours. Some deep-sea creatures have evolved to use these acoustic properties for navigation, creating sound maps of their environment that allow them to navigate in complete darkness. The bioluminescence at these depths operates on scales that dwarf anything we see in surface waters. Entire communities of organisms can create coordinated light displays that stretch for miles across the trench floor. These living light shows serve purposes we're only beginning to understand, from communication to predator avoidance to reproductive displays that can be seen from incredible distances in the eternal darkness. The creatures that inhabit these ultimate depths have evolved senses that seem almost supernatural. Some can detect chemical gradients so subtle that they can taste the direction of food sources from miles away. Others have developed electrical senses so sensitive that they can detect the heartbeat of other organisms from across the trench floor. The reproductive cycles of these deep trench organisms operate on timescales that make them seem almost immortal. Some species reproduce only once every few decades, timing their reproduction with rare geological events that might occur only a handful of times in a human lifetime. The larvae from these reproductive events can drift in the deep currents for years before settling into their adult habitat. The food webs that operate in these trenches are based on principles that seem to violate basic ecological laws. Entire ecosystems derive their energy from the decomposition of organic matter that has been falling from the surface world for thousands of years. This ancient organic matter, compressed and chemically altered by the extreme conditions, provides nutrition for communities that have been isolated from surface ecosystems for millions of years. The microbial communities that exist in the sediments of these trenches represent some of the most extreme life forms on our planet. These microorganisms exist in conditions that combine crushing pressure, near freezing temperatures, and complete darkness, yet they maintain active metabolisms that can process organic matter for thousands of years. Some of these deep sediment bacteria have been found to be virtually immortal, capable of repairing cellular damage faster than the extreme environment can cause it. These organisms exist in a state of biological equilibrium that allows them to survive conditions that would kill virtually any other form of life within seconds. The chemical processes occurring in these deep sediments create their own unique environments. The decomposition of organic matter under extreme pressure produces chemical compounds that exist nowhere else on Earth. These exotic chemicals support microbial ecosystems that operate on biochemical principles we're only beginning to understand. The discovery of active volcanic systems in the deepest trenches has revealed that our planet is far more geologically active than we ever imagined. These deep-sea volcanoes don't just create new seafloor, they generate unique mineral deposits and create chemical environments that support forms of life found nowhere else on Earth. The mineral deposits found in these depths contain concentrations of rare elements that could revolutionize modern technology. However, the environmental cost of extracting these resources could be catastrophic for ecosystems that have remained undisturbed for millions of years. The creatures living in these depths have no experience with the kind of disturbance that mining operations would create. The deep ocean currents that flow through these trenches don't just transport water, they carry with them the chemical signatures of the entire planet. These currents eventually return to the surface, bringing with them nutrients and minerals that have been processed in the most extreme environments on Earth. The carbon storage capacity of these deep trenches is staggering. The organic matter that accumulates in these depths represents one of the largest carbon reservoirs on our planet, storing carbon that has been removed from the atmospheric system for millions of years. This deep ocean carbon storage helps regulate Earth's climate over geological timescales. But this system isn't permanent. Changes in ocean circulation or chemistry could release vast amounts of stored carbon back into the atmosphere, potentially triggering climate changes that would affect the entire planet. The deep ocean represents both a climate stabilizer and a potential source of catastrophic change. The exploration of these ultimate depths requires technology that pushes every boundary of human engineering. The vessels capable of reaching these depths must be constructed to withstand pressures that would crush conventional submarines instantly. Every component, from the hull to the viewing windows, must be engineered to perfection. The psychological challenges of exploring these depths are as extreme as the physical ones. The journey to the bottom of the deepest trenches takes hours, during which explorers must cope with the knowledge that they are travelling to one of the most isolated and hostile places on Earth. The darkness outside is absolute, broken only by the artificial lights of the exploration vessel. The sense of isolation at these depths is profound. Communication with the surface is impossible through conventional means, and explorers are truly alone in one of the most extreme environments our planet has to offer. The weight of miles of water pressing down creates both physical and psychological pressure that can be overwhelming, yet those who have made this ultimate journey describe it as life-changing. To witness the alien landscapes of the deepest trenches, to see creatures that exist nowhere else in the universe, to experience firsthand the most extreme environment on our planet creates a perspective that fundamentally changes how you understand Earth. The scientific discoveries made during these deep trench expeditions continue to revolutionize our understanding of life itself. Each expedition reveals new species that challenge our basic assumptions about biology, geological formations that shouldn't exist according to current theories, and chemical processes that open entirely new fields of research. The organisms discovered in these depths don't just add to our catalogue of Earth's biodiversity, they expand our understanding of what life can achieve. The biochemical adaptations that allow these creatures to survive in such extreme conditions are being studied for applications in medicine, materials science, and biotechnology. The future of deep-sea exploration promises discoveries that will continue to reshape our understanding of our planet. New robotic systems are being developed that can explore these depths more thoroughly than ever before, operating in conditions that would be instantly fatal to human explorers. These automated exploration systems are revealing that the deepest parts of our oceans are far more active and dynamic than we ever imagined. The data they collect is showing us that the deep ocean plays a crucial role in regulating Earth's climate and supporting global ecosystems in ways we never understood. The deep ocean represents not just the final frontier on our own planet, but a window into understanding how life might exist elsewhere in the universe. The extreme conditions found in these depths closely resemble those that might exist on other worlds, making these earthly environments invaluable for astrobiology research. As we continue to explore these crushing depths, we're discovering that our planet still holds mysteries as profound as anything we might find among the stars. The deep ocean reminds us that the greatest adventures in exploration and discovery don't require travelling to distant worlds. They're waiting for us in the alien realm that exists right here, on our own planet, hidden beneath miles of crushing water in the eternal darkness of the abyss. The journey through these ultimate depths reveals that Earth is far more extraordinary than most of us ever imagined. In the crushing darkness of the deepest trenches, we find not just the physical limits of our world, but evidence of life's unlimited capacity to adapt and thrive in conditions that challenge everything we thought we knew about what it means to be alive on our remarkable planet. The ancient water trapped in these deepest trenches carries with it chemical signatures that tell the story of our planet's evolution. This water, isolated from the surface world for millennia, preserves the chemistry of oceans that existed when Earth was a fundamentally different planet. Scientists analysing this primordial water have discovered chemical compounds that haven't existed in surface waters for millions of years. The sediment cores extracted from these ultimate depths reveal climate records that stretch back further than any ice core sample. Each layer tells a story of ancient atmospheric conditions, massive volcanic eruptions, and extinction events that reshaped life on our planet. The deepest sediments contain evidence of the Great Oxidation Event, when early life forms first began producing oxygen, fundamentally altering Earth's atmosphere and setting the stage for complex life as we know it. But perhaps the most mind-bending discovery in these depths is the existence of what scientists call extremophile communities. These aren't just organisms that tolerate extreme conditions, they're life forms that absolutely require these crushing pressures and toxic chemical environments to survive. Remove them from their deep-sea habitat, and they literally fall apart, their cellular structures collapsing without the immense pressure they've evolved to depend on. The energy sources that power these deep-sea ecosystems operate on principles that seem to violate everything we learned about life in basic biology. While surface life depends on photosynthesis and the energy of sunlight, these deep-sea communities derive their energy from processes that would be instantly toxic to surface dwellers. They feed on hydrogen sulfide, methane, and other chemicals that seep from the Earth's core, creating biological processes that are completely independent of the sun. Recent discoveries have revealed underwater forests of bacterial mats that cover vast areas of the deepest ocean floor. These living carpets, composed of billions of microscopic organisms, create three-dimensional ecosystems that can be several feet thick. The bacteria in these mats work together in ways that seem almost intelligent, creating complex chemical gradients that support entire food webs of specialized organisms. The creatures that graze on these bacterial forests have evolved into forms that seem designed for an alien world. Some have developed multiple stomachs to process the complex chemicals in their bacterial diet, while others have evolved symbiotic relationships with the bacteria themselves, carrying colonies of microorganisms within their bodies like living chemical factories. The reproductive strategies employed by these deep-sea organisms push the boundaries of what we consider possible in biology. Some species have evolved to reproduce through a process called horizontal gene transfer, literally sharing genetic material with other organisms to create offspring that combine the survival traits of multiple parents. It's like sexual reproduction taken to an extreme that would be impossible in surface environments. Yet, the pressure at these depths creates chemical conditions that allow for biochemical processes that simply cannot occur anywhere else on Earth. The intense force compresses molecules in ways that create new chemical bonds, leading to the formation of organic compounds that exist nowhere else in nature. These pressure-formed chemicals support ecosystems that operate on biochemical principles we're only beginning to understand. The thermal dynamics of these deepest trenches create underwater weather systems that operate on scales both massive and intimate. Temperature differences of just a few degrees can create currents that transport nutrients and organisms across vast distances, while microscopic thermal gradients can determine where different species are able to survive within the same trench system. The discovery of active hydrothermal vents in the deepest parts of these trenches has revealed that the boundary between geology and biology becomes increasingly blurred at these extreme depths. The mineral deposits created by these vents don't just provide habitat for deep-sea organisms, they actually incorporate living bacteria into their crystal structures, creating hybrid formations that are part rock, part living organism. These living mineral deposits grow over thousands of years, creating underwater spires and towers that can reach heights of several hundred feet. The organisms embedded within these structures continue to live and reproduce, creating geological formations that are literally alive. It's as if the Earth itself has become a living organism in these deepest places. The acoustic properties of these depths create communication networks that span entire ocean basins. Deep-sea creatures have evolved to use low-frequency sounds that can travel for thousands of miles through the dense water of the abyss. These acoustic highways allow isolated populations to maintain genetic contact across distances that would be impossible for surface-dwelling species. Some deep-sea organisms have evolved echolocation systems that are more sophisticated than anything developed by surface animals. They can create detailed sound maps of their environment, navigating through complete darkness with precision that rivals the most advanced sonar systems. These biological sonar systems operate on frequencies that are perfectly tuned to the acoustic properties of the deep ocean. The bioluminescent organisms in these depths have evolved light-producing capabilities that go far beyond simple communication or predator avoidance. Some species can create complex light patterns that seem to serve as a form of underwater language, with different combinations of flashes and colours conveying specific information about food sources, mating opportunities, or environmental dangers. The chemical signals used by deep-sea organisms for communication operate on scales that dwarf anything found in surface ecosystems. Some creatures can detect pheromones and chemical markers from distances of several miles, creating chemical communication networks that connect organisms across vast areas of the ocean floor. The metabolic rates of organisms living in these extreme depths operate on timescales that make them seem almost frozen in time. Some deep-sea fish have metabolisms so slow that they age at rates measured in centuries rather than years. Individual organisms can live for thousands of years, making them some of the oldest multicellular life forms on our planet. The evolutionary pressures operating in these depths have created organisms that seem to exist at the very limits of what complex life can achieve. The cellular structures of these creatures are so specialized for extreme conditions that they represent entirely new categories of biological organization. Their proteins, enzymes, and cellular membranes all operate on principles that are fundamentally different from anything found in surface life. The discovery of multicellular organisms living in the deepest ocean sediments has revealed that complex life can exist in conditions that were once thought to support only the simplest microorganisms. These sediment-dwelling creatures have evolved to extract oxygen and nutrients from environments where both are incredibly scarce, creating biological processes that operate at the very edge of thermodynamic possibility. The deep ocean's role as a planetary life support system becomes even more apparent when we consider its function as a global chemical processor. The extreme conditions of these depths create chemical reactions that help regulate the composition of seawater throughout the entire ocean system. The deep ocean acts like a massive chemical filter, processing pollutants and maintaining the chemical balance that supports life throughout the marine environment. The carbon sequestration capabilities of the deep ocean operate on scales that dwarf any human-designed carbon capture system. The organisms living in these depths don't just store carbon in their bodies, they actively transport carbon from the surface world to the deep ocean, where it can be stored for thousands of years in sediments and mineral deposits. The deep ocean currents that flow through these trenches create a global circulation system that connects the deepest parts of our oceans with surface waters around the world. This circulation system transports not just water, but also nutrients, chemicals, and even microscopic organisms across vast distances, creating biological connections that span entire ocean basins. The magnetic properties of the deep ocean create navigation systems that some organisms use to traverse vast distances in complete darkness. The Earth's magnetic field interacts with the mineral-rich water of the deep ocean to create magnetic gradients that serve as underwater highways for migrating species. The pressure-induced chemical reactions occurring in these depths create their own unique periodic table of elements. The extreme conditions cause familiar elements to behave in completely unfamiliar ways, creating chemical compounds that exist nowhere else on Earth. These exotic chemicals support biological processes that operate on principles we're still trying to understand. The discovery of liquid mercury deposits in some of the deepest trenches has revealed that heavy metals can exist in liquid form at the bottom of our oceans. These liquid metal deposits create their own unique ecosystems, with specialized bacteria that can actually metabolize mercury and other heavy metals that would be instantly toxic to surface life. The deep ocean's role in planetary climate regulation extends far beyond carbon storage. The thermal mass of the deep ocean helps moderate global temperature changes, while the chemical processes occurring in these depths help regulate atmospheric composition over geological timescales. The deep ocean represents a planetary thermostat that has helped maintain habitable conditions on Earth for billions of years. The exploration of these ultimate depths continues to reveal that our planet operates on principles that are far more complex and interconnected than we ever imagined. The deep ocean isn't just a remote alien environment, it's an integral part of the planetary system that supports all life on Earth. As we push the boundaries of deep-sea exploration, we're discovering that the mysteries of the deep ocean are intimately connected to some of the most fundamental questions about life itself. The extreme conditions found in these depths may hold the key to understanding how life first began on our planet and how it might exist elsewhere in the universe. The technological challenges of exploring these depths continue to drive innovations that benefit far more than just ocean research. The materials science breakthroughs required to build vessels capable of withstanding these extreme pressures have led to advances in everything from medical devices to spacecraft construction. The future of deep-sea exploration promises discoveries that will continue to reshape our understanding of our planet and our place in the cosmos. As we develop better tools for exploring these crushing depths, we're beginning to realize that the deep ocean represents not just the final frontier on our own planet, but a window into understanding the fundamental principles that govern life throughout the universe. The journey through these ultimate depths reveals that Earth is far more extraordinary and mysterious than most of us ever imagined. In the crushing darkness of the deepest ocean, we find not just the physical limits of our world, but evidence of life's unlimited capacity to adapt, survive, and thrive in conditions that challenge everything we thought we knew about the possibilities for existence on our remarkable planet. The profound isolation of these ultimate depths creates conditions that challenge our very conception of what it means to be alive. In the crushing darkness of Challenger Deep, where the pressure would compress a human body to the size of a marble in milliseconds, we find organisms that have not just survived, but flourished for millions of years in conditions that seem to mock every law of biology we thought we understood. The water itself at these depths becomes something alien. Under pressures exceeding 1,000 times what we experience at sea level, the molecular structure of water changes in ways that create an environment more foreign than the surface of Mars. This isn't just deep water, it's a completely different substance, dense and heavy, with properties that exist nowhere else in our solar system. The creatures that call these ultimate depths home represent the absolute pinnacle of biological adaptation. The deepest dwelling fish ever discovered, ghostly snailfish found at depths exceeding 8,000 meters, seem to exist at the very edge of what complex life can achieve. Their bodies are composed almost entirely of specialized proteins and water, with no gas-filled organs that would collapse under the crushing pressure. These remarkable organisms move through the water like living phantoms, their transparent bodies barely distinguishable from the pressure-dense water around them. They feed on the sparse organic matter that manages to complete the impossible journey from the surface world, competing for resources in an environment where every fragment of nutrition represents a victory against the crushing forces of the abyss. But even these extraordinary fish are not the most extreme inhabitants of these depths. Amphipods, tiny crustaceans no larger than your thumb, have been discovered thriving in the deepest parts of the Mariana Trench, living proof that complex life can exist under conditions that would instantly destroy virtually any other organism on Earth. The Hadal amphipods represent one of the most successful adaptations to extreme environments our planet has ever produced. These remarkable creatures have evolved cellular structures that can withstand pressures that would crush steel, metabolic processes that operate efficiently in near-freezing temperatures, and sensory systems that allow them to navigate and hunt in complete darkness. The microbial communities that exist in the sediments of these deepest trenches push the boundaries of what we consider possible for life itself. These microorganisms exist in conditions that combine crushing pressure, toxic chemistry, and complete isolation from the surface world. Yet they maintain active ecosystems that have been operating continuously for millions of years. Some of these deep sediment bacteria have evolved to become virtually immortal, capable of repairing cellular damage faster than the extreme environment can cause it. They exist in a state of biological equilibrium that allows them to survive conditions that would kill virtually any other form of life within seconds of exposure. The chemical processes occurring in these ultimate depths create environments that seem pulled from science fiction. The intense pressure causes dissolved gases to behave in ways that create underwater rivers of liquid carbon dioxide flowing along the trench floor, like ghostly streams. These chemical rivers support their own unique ecosystems, with organisms that have evolved to extract energy from processes that would be instantly toxic to surface life. The geological violence that shapes these deepest places operates on scales that dwarf anything we witness on land. Underwater earthquakes can trigger massive landslides that move billions of tons of sediment across vast distances, burying ancient ecosystems and creating new ones in their wake. Yet somehow, life persists through these catastrophic events, adapting and recovering in ways that seem almost miraculous. The hydrothermal vents that dot the deepest parts of these trenches create oases of life in what was once thought to be a biological desert. These underwater geysers, shooting superheated water rich in chemicals that would be toxic to surface life, support ecosystems that rival tropical rainforests in their complexity and diversity. The organisms living around these deep-sea vents have evolved biochemical processes that seem to violate the fundamental principles of biology. Giant tube worms, some reaching lengths of 8 feet, have no digestive systems whatsoever. Instead, they host colonies of bacteria within their bodies that convert the poisonous chemicals from the vents into usable energy. The discovery of these chemosynthetic ecosystems has revolutionized our understanding of how life might exist elsewhere in the universe. The extreme conditions found around these vents closely resemble those that might exist on other worlds, particularly the subsurface oceans of moons like Europa and Enceladus. The bioluminescent displays in these ultimate depths create light shows that would put any surface phenomenon to shame. Entire communities of organisms can coordinate their light production to create displays that stretch for miles across the trench floor, pulsing and flashing in patterns that serve purposes we're only beginning to understand. The acoustic environment of these depths is equally alien. Sound waves travel differently through the pressure-dense water, creating acoustic conditions that allow communication across vast distances. Some deep-sea creatures have evolved to use these acoustic properties for navigation, creating sound maps of their environment that allow them to traverse the eternal darkness with remarkable precision. The reproductive strategies employed by these extreme depth organisms operate on timescales that make them seem almost immortal. Some species reproduce only once every few decades, timing their reproduction with rare environmental events that might occur only a handful of times in a human lifetime. The food webs that operate in these deepest trenches function on principles that seem to defy basic ecological laws. Entire ecosystems derive their energy from the slow decomposition of organic matter that has been falling from the surface world for thousands of years, creating biological communities that are completely independent of sunlight. The pressure at these ultimate depths doesn't just affect living organisms, it fundamentally alters the behavior of matter itself. Chemical reactions that are impossible at surface pressures become routine in these extreme environments, creating conditions where new forms of chemistry support entirely new forms of life. The exploration of these deepest places requires technology that pushes every boundary of human engineering. The vessels capable of reaching these depths must be constructed to withstand forces that would crush conventional submarines instantly, using materials and techniques that represent the absolute pinnacle of human technological achievement. The psychological challenges of descending to these depths are as extreme as the physical ones. The journey to the bottom of the deepest trenches takes hours, during which explorers must cope with the knowledge that they are travelling to one of the most isolated and hostile places on our planet. Yet those who have made this ultimate journey describe it as profoundly transformative. To witness firsthand the alien landscapes of the deepest ocean, to see creatures that exist nowhere else in the universe, to experience the most extreme environment our planet has to offer, creates a perspective on Earth that fundamentally changes how you understand our world. The scientific discoveries made during these deep trench expeditions continue to revolutionize our understanding of life itself. Each expedition reveals new species that challenge our basic assumptions about biology, geological formations that shouldn't exist according to current theories, and chemical processes that open entirely new fields of research. The future of deep-sea exploration promises discoveries that will continue to reshape our understanding of our planet and our place in the cosmos. New robotic systems are being developed that can explore these depths more thoroughly than ever before, operating in conditions that would be instantly fatal to human explorers. As we continue to push the boundaries of deep-sea exploration, we're discovering that the mysteries of the deep ocean are intimately connected to some of the most fundamental questions about life itself. The extreme conditions found in these depths may hold the key to understanding how life first began on our planet and how it might exist elsewhere in the universe. The deep ocean represents not just the final frontier on our own planet, but a window into understanding the fundamental principles that govern life throughout the cosmos. In the crushing darkness of the deepest trenches, we find evidence of life's unlimited capacity to adapt and thrive in conditions that expand our understanding of what it means to be alive. The journey through these ultimate depths reveals that our planet still holds secrets as profound and alien as anything we might discover among the stars. The deep ocean reminds us that the greatest adventures in exploration and discovery don't require travelling to distant worlds. They're waiting for us right here, hidden beneath miles of crushing water in the eternal darkness of our own planet's most extreme frontier. The profound realization that emerges from our journey through those crushing depths is that we have barely begun to understand the planet we call home. Every expedition to the deepest parts of our oceans reveals that Earth operates on principles far more complex and interconnected than we ever imagined. The creatures we've encountered in these ultimate depths represent evolutionary achievements that push the very boundaries of what we thought life could accomplish. They've solved problems that our most advanced technologies struggle with, creating biological solutions to extreme pressure, toxic chemistry, and complete darkness that seem almost supernatural in their effectiveness. The deep ocean's role as a planetary life support system becomes more apparent with every discovery we make. The chemical processes occurring in these crushing depths don't just support the alien ecosystems we've explored, they actively regulate the chemistry of the entire ocean system, maintaining the delicate balance that allows life to flourish throughout our planet's waters. The thermal regulation provided by deep ocean currents helps stabilize Earth's climate over geological timescales. The carbon storage capacity of the deep ocean dwarfs any human-designed system, effectively removing vast amounts of carbon dioxide from our atmosphere and storing it in the crushing depths where it can remain locked away for thousands of years. But perhaps the most humbling aspect of our journey through these depths is the realization of how little we actually know. We estimate that we've explored less than 5% of our oceans, leaving 95% as a complete mystery. Entire ecosystems could exist down there. Mountain ranges larger than the Himalayas, canyons deeper than anything we've discovered, and we would have no idea they're there. The technological challenges of exploring these depths continue to push the limits of human engineering. Yet each breakthrough reveals that we're still only scratching the surface of what lies beneath. The robotic systems we're developing to explore these crushing depths represent some of the most advanced technology ever created, yet they can only provide us with glimpses of the vast underwater universe that surrounds us. The implications of what we're discovering in these depths extend far beyond marine biology or oceanography. The extreme conditions found in the deepest parts of our oceans provide natural laboratories for understanding how life might exist elsewhere in the universe. The organisms thriving in these crushing depths offer templates for what we might find in the subsurface oceans of distant moons or the extreme environments of other worlds. As we continue to develop better tools for exploring these depths, we're beginning to realize that the deep ocean represents not just an unexplored frontier, but a fundamental part of our planet's operating system. The deep ocean doesn't just exist alongside the familiar surface world. It actively shapes and maintains the conditions that make surface life possible. The journey through the crushing depths of our oceans reveals that we live on a planet far more extraordinary and mysterious than most of us ever imagined. In the eternal darkness of the abyss, where pressures would instantly crush any surface dweller and temperatures hover just above freezing, we find not emptiness but abundance, not death but life, in forms so alien they expand our understanding of what existence means. The deep ocean reminds us that Earth still holds secrets as profound as anything we might discover among the stars. The greatest frontier for exploration and discovery isn't found in the vastness of space, but in the crushing depths of our own world's oceans, where alien landscapes and impossible creatures wait in the darkness for brave explorers to uncover their mysteries. In the end, our descent through the layers of the ocean has revealed that we are inhabitants of a water world where the familiar continents and surface seas represent just a thin skin on a planet dominated by the alien realm of the deep. The crushing depths we've explored contain more livable space than all the land on Earth combined, yet they remain almost completely unknown to us. The ocean's deepest places challenge everything we thought we knew about our planet, revealing that Earth is far stranger, more alien, and more wonderful than we ever dared imagine. In the crushing darkness of the abyss, we discover not just the physical limits of our world, but the limitless possibilities for life to adapt, survive, and thrive in conditions that redefine what it means to be alive on our extraordinary planet.